So yeah, I'm going to be talking about embedded Elixir and friends with Nerves. It's the CodeBeam conference. So Nerves is Elixir first, and as far as the tooling and everything is in Elixir, and we fully support Elixir. But obviously, being a Beam language, you can also compile your Erlang or LFE or whatever else and run it in a Nerves application. So the first thing I want to talk about a little bit is why Elixir is a great language for embedded, and also, Erlang, the whole Beam family is great for embedded. The first point is that the Beam and the Beam ecosystem are embedded first to begin with. So here's a picture of one of the Ericsson switches where Erlang was first used, sporting a 10 gigabit to 160 gigabit per second switching throughput. There's probably people in the room here that could answer this question, but I was curious if only the main processor runs Erlang or all the actual fabric switching uses Erlang. Nobody knows. Sure. Yeah, so only the main two processors run Erlang, right? Okay. Yeah, so it sounds like the data path is not Erlang, but the control path is Erlang, controlling all the ASICs and things. That's what I was guessing was true. So here's a picture of one of the redundant main processor boards running Erlang, probably just on the one chip here. And then the backplane would be the high-speed, silicon level packet switching and things. And it's no surprise that our current embedded systems are powerful enough to run the Beam, because these control plane circuits were not super powerful at the time compared to today's hardware. The other thing I want to talk about here with Elixir for embedded is that we get a lot of baked-in fault tolerance from OTP Erlang roots. And the point here is that this is not what they meant when they said let it crash. This is a completely different thing that you don't want to let happen. These are your Windows blue screens of death. If you would like to see more of these, there's Kevlin Henney's Twitter stream is where I got these from. He collects these artifacts for your viewing pleasure. So another thing that we have with Elixir for free is this lightweight concurrency model, so that you don't have to invent all the things from scratch to be able to make use of all of your cores, whether you have 4 cores or a lot of cores on your server or your embedded device. We also get process level fault tolerance, which is important for an embedded system so that you can localize your failures. I also want to talk about, with lightweight concurrency, we have the per process garbage collection, which becomes very important. And we also have immutable data structures, which helps with that garbage collection to be more efficient. This is just a quick figure that I got from this blog below about visualizing how the Erlang, the memory model works. And then I want to compare, this is what a memory utilization graph for the JVM would typically look like, with the shaded purple part being the part that's wasted because it's things that need to be collected and haven't yet, so garbage. And if you've worked in operations, this is a pretty typical JVM graph where there's a steady state of used memory, and then it goes up and down as it hits the point where it needs to do a full GC. If you zoom in a little bit, you'll see that it also is continuously doing incremental garbage collections along the way, and that's the concept of a young generation and an old generation, where when you first create an object, there's a good chance that you're going to delete it immediately, whereas if it survives for a while, then you need to wait for the big bang, delete a lot of things. This is, by comparison, the Beam memory utilization graph under constant load. I would love for somebody to tell me that I'm lying, but so far no one has when I've presented this. It's a lot more steady, and I think the reason for that is that we have the per process garbage collection, where we have mostly short-lived processes that accumulate memory over time as they're using it. There is still garbage, and we still have the incremental garbage collection. We also have the old generation garbage collection. But then at the end of the process, you just drop all the memory, and since we have immutable data structures, we know when your process is done, all the memory that process needed is available to free, because no one else could be sharing a mutable copy of it. So what this gives you is, probabilistically, at any given time, a lot of processes are accumulating a little bit of memory, and some processes are losing all of their memory. So over time, it's flat. So the next thing that I want to talk about real quickly with Elixir and also Erlang is this concept of binary pattern matching, which is important for embedded systems. In this contrived example, I have we're decoding something that has a 3-bit operation code, 6 bits of address data, and 7 bits of data into just this tuple there. And this is commonly something you see in a data sheet where it describes 2 bytes of data that you're going to get back across the wire, and you have to interpret it like this. It's very simple to do that with pattern matching. And then you read further on in the data sheet, and it says, by the way, if those first 2 bits are zeros, then you're in extended address mode. So now 9 bits of the data are the address, and 4 bits are the data. And when you're using Elixir, it's very easy to just add another function head, and you're done, rather than having procedural, looping through each bit or something like that and branching off. Another thing that we get out of our ecosystem is this embedded IoT platform, where you have perhaps Erlang, Elixir, whatever, running on your device, but then you also have it running on the server that they're all connecting to. This is a picture of what your server looks like as all of your IoT devices are simultaneously connecting to it. And then, so if you want to, you can use, like I mentioned, you can use Elixir and Phoenix on your server, or you can use Elixir and Nerves on your headless device that doesn't have a screen. And then you also get, Phoenix comes with the JavaScript client for speaking channels to the back end. So I wanted to talk about several options for embedding Elixir. On the left here, we have Grisp. I went to the Grisp training the other day, and it was interesting to really learn more about the details of how that works. With Grisp, you don't have a Linux operating system. You actually just have a compiled binary with an RTEMS operating system baked into the binary itself. Whereas with Nerves in the middle here, you have it running on Linux, but it's a very minimal Linux. And then on the right, you have just your off-the-shelf Raspberry and Linux or Windows or whatever you want to install on your embedded device, and then you just run, install Elixir on top of it as if it were a server. So the option on the right, well, of course that will work. I mean, you're just installing a regular server and then you're putting Elixir on top of it. But it comes with all the normal issues that you have administratively as far as deploying and packaging your application and the operating system itself, locking things down. It has relatively long boot times for an embedded device because it has to load up, the entire operating system or however much of the stripped-down operating system that you want to manage yourself. And then typically you also have a read-write file system, which becomes a problem if you suddenly pull the power on the device while it's writing to the hard drive. Then your file system's potentially corrupted, and then it won't boot next time, which would be a sad day. On the other side of the spectrum, you have Grisp, which runs on this evaluation board, and then you could also develop your own board that it would run on. But in this case, you have purpose-built hardware, and you get the real-time as a term is maybe something you are or not familiar with. But if you're in embedded systems, real-time is a thing that you would know that you had that requirement if you had that requirement, and you need this for that because Nerves is not real-time. So now I want to talk a little bit about Nerves. Our tagline is crafting and deploying bulletproof embedded software in Elixir. And basically what we do is we put Elixir on a Raspberry Pi. And there you go. That's Nerves. So Nerves uses Buildroot to build a minimal Linux with all the drivers and things that you need for the supported hardware. We support commodity or custom hardware, but you need to do a little bit of work for your own custom hardware, obviously. We kind of treat Beam as the operating system. So we also have Linux as the operating system, but we have a very stripped-down Linux and depend on you to run your own things on top of that. As I mentioned, we have a read-only file system, which protects you against corruption when you lose power. And then we have these firmware artifacts for deployment and updates. This is sort of self-explanatory, where on the left side you have a standard Linux distribution that includes all the drivers and all the applications and things that the distribution decided you should have. And on the right, we have Nerves as a minimal version of that with only the drivers that you need for the board that you're actually going to run on. And we call this a Nerves system. Is this little package of things that's, for example, just for a Raspberry Pi Zero. It's only the things that you would need to run on a Raspberry Pi Zero with the Beam. And then we call this a Nerves firmware that includes your Beam application. And then I have daemons in quotes here because you can include other binaries that you want to run that are not there in the normal nerve system that the official team maintains. But you would need to start them from your app. They wouldn't be started by an init process. Because Erlinit here is replacing systemd and the regular, oops, that's fine. Erlinit replaces systemd, so there is no init process other than just a little C program that starts the beam. There's also a thing called a nerves toolchain. That's the process that cross-compiles your code so that it runs on ARM, for example, even though your laptop is running x86. And there's one of those for each system. We also have a read-write partition that you can write your application data to, since the main firmware is read-only to protect you against corruption. And then we have a writable B firmware slot that you can write an updated firmware to and then boot into it. And then you can make sure that it works before you decide that that's going to be the one you keep using. We have support for a lot of targets officially out of the box. There's all the Raspberry Pi family and the BeagleBone family and the Lego EV3, which is pretty exciting that you can run nerves and the beam on Legos. We also have application level fault tolerance with a thing called shoehorn. Tagline is get your boot on. So the thing here is that it configures your network and starts some initial management tooling. It formats the partitions, basically a lot of the things that your operating system would normally do for you. And then it starts your app. So that way, if you have something in your application that fails to start the beam, at least it's up enough that you could push a new firmware to it. It's very handy in development. It used to be called bootloader, but it's not a bootloader, so that was confusing to people, surprisingly. Yeah, so in summary, Nerves is really well integrated with Elixir. We have all the regular mix tools there, a generator, deps.get, and then we have this thing called firmware to cross-compile your code into a firmware. And then you can either burn it to an SD card or push it over the network to the device to update it. This is kind of a prototypical example of something that we developed at Latote, where we have, for example, a Raspberry Pi with actual hardware that's talking to an application that's written, with Phoenix and Nerves running on your device, and then like a Chrome web engine that's running a JavaScript application that displays on the screen, all in your Raspberry Pi, and then it talks to the servers in the cloud. But the magic bit here is that if I step forward a slide, you're kind of like, wait, what even changed? This is running on your laptop now, and you're using IEX to control mock hardware that doesn't actually exist, running a Phoenix app in development on your laptop, and then you're talking to Chrome that's displaying your browser, and then you talk to the local development server on your laptop. So the magic there is that now I don't need real hardware to develop the UI application and interact with the hardware and test things. And for example, if you're working with a barcode scanner in real life, I can pretend to scan a barcode using IEX. Just stepping back, remember that the Nerves firmware includes the Nerves system and then your application. I want to talk for a second about custom Nerves systems. We have tooling here and documentation about how you can run this mix Nerves system shell command that puts you into a Docker container so that you can build a custom system using the Linux build root tools. You have to be running Linux to do this, so that's why we run it in Docker if you're on a Mac or Windows or some other platform. And then I just wanted to show that it's not super scary to use these GUI tools to like search for. I want to include this package that's not normally in the normal systems. And then at the end of the day, it ends up just adding this line to a config file, and then you check it into Git, and you compile it, and then you have your own custom Nerve system. It's not super scary. But you may not need a custom system, because if you just want to, for example, put a file on there, you can use something called a rootfs overlay, which, as the name implies, the normal Nerve system has some file structure here. If you want to put an etc hosts file onto that thing, you don't have to change the official Nerve system. You can just overlay this on top of there, so that then your firmware will have that file in it. I want to mention real quickly that a big selling point for Nerves is our overwhelmingly welcoming and helpful community, is the tagline that I'm trying to sell here. For example, I've been manually inviting everybody and welcoming everybody to the Nerves channel on the Elixir Lang Slack, and people have responded really well to that, and they really get engaged and want to talk about their questions and their projects. I think that's great. The Slack channel has seen pretty good growth over the past couple of years, from 500 up to 1,500 people. And we're also branching out to the Elixir forum and other venues where we can engage with the community where they're at. So I just want to point out that if anyone wants to get involved, you can contribute to the project. I initially wanted to get involved even though I was new to Elixir at the time. But then I realized that I have a lot to contribute because I was new to Elixir. I can communicate the things that I don't know. How can I make this more clear? How can I make the guides better? So if anybody's sitting here not knowing what nerves is today, and they would like to know what nerves is and get deeper into it, please reach out, and you can be a huge help. So I want to talk a little bit about this eye application. So I have this Raspberry Pi Zero with the official case and the official camera, and it connects over a USB port here. I'm going to be streaming video with the PyCam library and scanning barcodes with the ZBar library. ZBar is just an off-the-shelf application that someone else wrote, but I wrote this Elixir wrapper around it that lets you use it with nerves. I'm also using GraphQL subscriptions, which is a fancy buzzword that people like, and Phoenix channels, because why not? There's this thing called Nerves Init Gadget that makes it really easy to make a USB gadget device using nerves. So that what that means is that you can plug this into your laptop and it acts like a device on the USB interface as opposed to just providing power. So you can also provide composite devices here where it can act like an Ethernet and a serial port and whatever you can make with a USB device. I'm using Poncho projects here, which is different than an umbrella project in that umbrellas protect you only from the top. Ponchos protect you on all sides. So it's kind of a tongue-in-cheek thing. But basically, a Poncho project is just you make a directory instead of generating an Elixir umbrella project. And then you generate a bunch of projects in that folder, and then they just use path dependencies to connect with each other. And that's important with nerves because we don't want to use the default umbrella configuration process where it includes all the configs using a glob. We would rather have better control over, I want to apply this config and then this config. See the forum if you're interested in how config works in Elixir. So this is the application structure that I want to propose, is that we have an eye application for this camera that has all the business logic about managing the camera functionality itself. And we have an eye UI application that depends on that business logic that would be the interface to your application. Because as my good friend Lance would tell us, Phoenix is not your application. So all the Phoenixy things are in the IUI area. And then since we're using GraphQL and Phoenix channels and subscriptions, all that stuff's in the UI. And then the eye application is just responsible for the actual camera and barcode things. And then similarly, we have nerves that comes in with an eye firmware application that's mostly nerves code. You don't have to actually write a whole lot in there. But it brings in the nerves dependency and the nerves init gadget that I mentioned. And then nerves network manages your network interfaces. And like I mentioned, you don't have to worry about most of that code. It's just nerves things that you only have to configure or tweak a little bit. And then speaking of config, an important thing here is that the eye application is configured to use a fake version of the camera. And then similarly, when you're running the eye UI application, you also want to use a fake camera because you're not on the device itself. And then if you're running the firmware application but on your laptop, which is the host target, we also use a fake camera. But then in the magical case where you're running the firmware on an actual Pi Zero, then we use the real camera module. This is just a real quick example of you can use the fake camera to set the image that you want it to pretend to present, and then it will pretend to stream that picture over and over. And then you can use the barcode scanner to say, scan the next barcode that you see, and you get the data back in IEX. Similarly, you can run the IUI application on your laptop, and you can get to the graphical thing if you've used GraphQL. And yeah, I want to show real quick in my last minute here how the thing works. First, I want to tell you that I'm sorry that I've written this JavaScript, and most of it's too terrible to show you. But if you haven't used channels or GraphQL subscriptions, I just wanted to give you a quick intro to, there's a GraphQL query if you're familiar with GraphQL, but instead of query, it says subscription, and that means that we're going to do a query, and then anytime something changes, just send me the updated value. If you want to know more, And if you want to build this thing yourself and take some hardware home, come see me at ElixirConf US, and we're going to do a one-day training on this thing. And that is the end of my presentation, but I want to show you. Hang on. This thing. So this is the streaming camera here. And then if I point it at a QR code, it will tell you what data is in the QR code. It's amazing. There's 2 QR codes on the screen. All right, I'm done.